All right, so one of the details that we've talked about with our non-contact forces, and so we said there's three non-contact forces that we sort of deal with in introductory level physics: the gravitational force, the electric force, the magnetic force. And we said all three of those contact forces, the real key underlying them is the idea of a field. And so what we're going to do is we're going to build off what we know from Coulomb's law about the electric force between point charges to talk about electric fields. So the first question becomes, well, how do we learn about the electric field? And so what we're going to do is we're going to start with a charge. In this case, I'll just happen to call it capital Q. So here's some charge. I'm going to place a test charge at a point P. So here's some point P. I'm going to place my little test charge, and again, the test charge I'm going to call Q naught here. And I'm going to see what force my test charge feels. So basically, I find out about the field by probing a particular point in space with a test charge. So in this case, let's just assume that this happens to be positively charged, this happens to be positively charged. I know that my test charge would be repelled by big Q, my source charge, and so I'd feel a force that points off in that direction. So the reason this becomes useful is that we define the electric field to be the force felt by our test charge, where then we divide out the test charge. So it doesn't matter. The fact that we're dividing out our test charge means that it doesn't matter what charge we use. Our force is going to depend on two charges. It's going to depend on both the source charge and the test charge. But we're dividing out the test charge so that the electric field just depends on the source. And so what this will do is basically it says at any particular point in space, so here at our point P, there is an electric field created by our source charge. When you place a test charge, some other charge at that point, it then it responds to that electric field by feeling an electric force. That's the idea. So there's sort of two ways that we can look at this equation. One is, again, the way that we've sort of defined it in terms of the electric field, and then the other is just rearranging it so that now we have the electric force is equal to whatever our test charge is times the electric field. And so in either of these two versions, let's think about what this equation tells us about how these two concepts relate, the electric field and the electric force. So for starters, we can use this equation just to think very simply about units. So the electric field has to have units of, well, force has units of newtons, charge has units of coulombs, so the units for the electric field, one way to write them is just newtons per coulomb. If I then think about this equation, well, here I've got two vectors, right? The electric force is a vector, the electric field is a vector, and I get the electric force by taking the electric field and multiplying it by some scalar. I know that if this is positive, then these two things will point in the same direction, just from the rules that we learned last semester about how two vectors relate if you take a vector and multiply it by a scalar. So if my test charge is positive, then the electric field will point in exactly the same direction as the electric force. If my test charge is negative, then the electric field and electric force point in opposite directions. So part of what we're going to do, and again, this is kind of the big point off of this slide, part of what we're going to do is we're going to say, hey, you know what, we're pretty good at thinking about the electric forces between charges. So to think about the electric field, we're actually going to start by thinking about the electric force on a positive test charge, because the electric force on a positive test charge will point in exactly the same direction as the electric field. So this is sort of the scheme we're going to use, is that when we're trying to figure out what the electric field is doing, we're always going to use a positive test charge to try and do that. All right, so The way that we're going to learn then about electric fields is, again, let's say here's my source charge. So come back and applying this. Here's my test charge. I put it at the point P where I'm interested in the electric field. I know that my positive test charge will be repelled by my positive source charge, so it's going to feel an electric force that points away from the source charge, which tells me that the electric field has to point away from the source charge. So again, the idea is that since I'm using a positive test charge to probe the field, the direction of the field will be in exactly the same direction as the direction of the force on my positive test charge. So this tells me that the electric field at point P points away from my positive source charge. If I flip it around and make my source charge negative, well, again, I want to probe the electric field at point P, so I'm going to start by putting a positive test charge at that point. I know that that positive test charge will be attracted towards the negative source charge. So the electric force is going to point towards my negative charge. Again, since I used a positive test charge to probe the field, the electric field and the electric force are going to point in the same direction. So the electric field will also point towards my negative source charge. So we can take this information and the equation that we've got and put together what we know about the electric field. So for a point charge, we know the electric force between two charged particles, and again what we're going to do is say, hey, Q here is our source charge, Q naught is our test charge. And again, your book does this with Q and Q prime. I'm simply using Q naught because it's easier to write within PowerPoint than Q prime is. There's not a really good prime symbol. So I'm using Q naught. It's exactly the same as your book using Q prime. It's just the test charge. They're separated by a distance r. Here's what I know from Coulomb's law about the magnitude of that force. Here's what I know about how the electric field will relate to that force. And so what this tells me is a couple of things. One, it says, well, I'm just dividing out the contribution of that charge. And since we're probing the electric field with a positive test charge, it doesn't really matter whether or not this is in absolute values. What I'm left with is that the magnitude of the electric field vector is going to be my Coulomb's constant, K, here I've included the sub E. Absolute value of my of my source charge, right, the charge that's causing the electric field, over r squared. And r now is the distance from your source charge to the point P that you're interested in. So we've sort of, in dividing out the test charge, we've kind of redefined what r is. We also know that the electric field, in exactly the same way that we said the electric force lies along the line between the two charges, the electric field, this equation says, well, it's got to lie along the same line. So it's got to lie along the line between my source charge and the point P I'm interested in the electric field. What we saw on the previous slide is that the electric field will point away from positive charges and it will point towards negative charges. So these are sort of the, kind of the basic rules that we've picked up here in terms of how to calculate the electric field due to point charges. So if we come back and think about, so I've got my positive source charge here, and I'm thinking about the electric field at point P, there's a couple of things that I can say that I now know. So one is, it's directed along the line connecting point P to the charge. It points away from the positive charge, and it has this particular magnitude. So again, here R, notice, is the distance from the charge to the point P. So we've redefined what R is here. So here's my expression for the magnitude of the electric field, and I know that it's going to point away from a positive source charge. If I've got a negative point charge, well, everything, again, I'm going to have an electric field vector that now points towards my charge. It's going to be, that electric field will be directed along the line connecting the charge to point P. It will point towards the negative charge, and I'll calculate the magnitude exactly the same way. So the absolute value here says I don't care whether this is a positive or negative charge. I'm still going to get a magnitude with the same value, as long as that charge is the same. So the last piece to add to this then is what happens if I have multiple point charges. And so if I've got multiple point charges, again, I'm just adding vectors. So here at point P, I've got two charges I'm interested in their contributions to the electric field at point P. I know that the contribution from my negative charge will point towards it. So the electric field will point at point P. The contribution to the electric field at point P from my negative charge will point towards the negative charge. The contribution to the electric field at point P from my positive charge will point away from. So what we're going to do is, again, we're going to figure out what the electric field, the contribution is from each of our individual point charges, and then we just have a vector addition problem. So in this case, the vector sum is going to point something about like this. Again, notice it's just a vector summation problem. In this case, I've got two-dimensional vectors. I've got stuff going on horizontally, stuff going on vertically. So I can pick whatever coordinate system I want. I've got two-dimensional things. I need to add those two vectors together. I'm going to have two equations to do it. So critical that we understand, the electric field is a vector field. You pick a point P, and the electric field there can be represented by some vector. That vector is going to tell you about the magnitude and the direction of the electric field. In terms of our point charges, again, we said those are 1 over r squared. So the farther you go away from the point charge, the weaker the electric field gets. So magnitude and direction, just like with any vector. And then if you want to figure out the electric field at point P, all you need to do is add together the contributions from all the source charges. So we're going to sort of focus on situations where we have multiple point charges, but we'll talk about, and we'll see that it's not any different if you have continuous distributions of charge. You just have to add together the contribution to the electric field from all the charge smeared out over your particular source charge. All right, so this is the idea that we're going to spend next couple of days in class really sort of working with. It's the electric field.